Let us begin our discussion on how to extract information from the wave function. We should let us start with with the with some restrictions that are necessary on the wave function. There are some conditions that the solution of Schrodinger equation, that is the wave function, should obey so that it is an acceptable wave function for matter wave. Okay, so what are these restrictions or what are these conditions? One of them is this normalization of the wave function. What is the idea of normalization? We have already discussed the probability interpretation of wave function. Let us start with that. For the convenience, let us start with the one-dimensional situation. We will also generalize into three dimensions. And this idea of normalization, I will first discuss by assuming that the wave function has no time dependence. Or in other words, I assume that we are trying to normalize the wave function at time 0. Okay, what happens at a later time when the wave function evolves with time? This we will discuss slightly later. So consider that we are discussing the normalization of the wave function at time 0. So consider in the one-dimensional case, suppose a particle is traveling along the x direction, positive x-axis. Let us say there is some point here, x, okay, and and we want to find out what is the probability of finding the particle in different regions of this x-axis. Now, this probability in this situation, this probability function is a continuous function. Okay, then it means that we cannot pick out a single point x because position itself is a continuous variable. So it means that we cannot say identify a point x1, x2, x3 or x and talk about the probability of finding the particle at that point. It's not possible. So what is possible is if there is some point x, what we can do is consider a small region of width, let us say dx, where dx is very small, dx can tend to 0. So consider a small region of width dx around the point x, and we can think about, we can define what is the probability of finding the particle in this small region dx. Not at exact point x, but in this small region dx around the point x. Okay, how do we proceed to do this? The value of the wave function at this point, let us say psi of x. Okay, then mod psi of x square. This is the probability density, or in this case it is probability per unit length. In the one-dimensional case, we define this as probability per unit length, or probability density is probability per unit length. If the particle is moving in a plane, in the two-dimensional situation, probability density is there will be two variables here, x comma y. Psi depends on x and y, or r and theta, depending upon the coordinate system that we are using. The probability density means probability per unit area. In three-dimensional motion, psi depends on three variables, x, y and z. Then probability density is probability per unit volume. Okay, so let us consider this one-dimensional case. So psi x square is probability per unit length. Then what is, you multiply this with this small length dx. So this is probability per unit length. Multiplying it with a small length dx, what you get is probability. So this is probability of finding the particle around the position x. Probability around the position x at some time. Okay, I have not discussed time factor. Let's assume that this is the value of the probability of finding the particle around the point x at time 0. Okay, we will bring in time a little later. So this is probability around x. Now we can ask the question, what is the probability of finding the particle between the points A and B? Okay, x equal to A and x equal to B. If this is the probability around the point x, what we can do is from A to B in this region, we can divide into such small length dx. Okay, for example, this is one such slice. Okay, similarly we can divide this region into different dx. Okay, this is one value of dx, and consider similarly the next region. Okay, let us say around the midpoint you have another point, so have another wave function. I mean the value of the wave function at this point, let's say consider this point. Okay, here the value of wave function will be different. So probability density will be different, but you are multiplying with the same length dx, where dx is very small. So you get another value of psi x square dx here, similarly mod psi x square dx here, etc, etc. So what is the total probability of finding the particle between A and B? It is mod psi x square dx at this section, mod psi x square dx at this section, mod psi x square dx at this section, etc. So it's a summation. Now in the limiting case, when dx tends to 0, this summation can become an integration. Okay, so the probability of finding the particle between the points A and B, let me use the symbol probability P between A and B, is an integral from A to B of this mod psi x square dx. So this is not a constant. The mod psi x square is not a constant. Its value can be different here. Different values of x, its value can be different. Okay, it need not be uniform. In general, it is different. So you are just adding mod psi x square dx, probability of finding the particle around this point in a small region dx here, mod psi x square dx here. So you are adding these small probabilities together. That's what this summation is, or this integration is. So integral A to B mod psi x square dx, adding the two, all the probabilities between the points A and B. Okay. Then we can ask the question, let us say this is our entire x-axis, okay, extended from minus infinity to plus infinity. Okay, we can ask the question, what is the total probability of finding the particle along the entire x-axis? So if this is the probability of finding the particle between the points A and B, what is the total probability of finding the particle along the entire x-axis? You are just extending A to minus infinity, B to plus infinity. So the total probability is integral minus infinity to plus infinity of this thing, this summation. You are dividing, but basically what you are doing is you are dividing this entire x-axis into small sections of width dx. In each width you find this wave function and you multiply with mod psi x square you find and multiply with dx. Okay, so and you are adding all the probabilities. So this is the total probability of finding the particle along the entire x-axis. And what is the value of this probability? If you take a measurement of the position of the particle, it will be somewhere along the entire x-axis. Okay, it can be somewhere along the entire x-axis. We don't know where it is, but it can be, we are sure that it can be somewhere along the entire x-axis. The chance of finding the particle when you take a measurement of its position is 100%. Because if you suppose you have some detectors along the arranged along the entire x-axis and you take a measurement of the position of the particle, then you are sure that one of the detectors will click, one of the detectors will record okay, the particle is here. Okay, so this is a certainty, that is any measurement of position of the particle will return some position along the entire x-axis, that is 100% sure. So that means this total probability of finding the particle along the entire x-axis must be 100%, or in numerical value this should be equal to 1. If you convert into percentage, multiply with 100, you get 100%. So it's not a fraction, it should be exactly 1. So this is the total probability of finding the particle along the entire axis is total probability. Okay, so this means total probability is equal to 1, and this is called normalization condition. This is called the normalization condition of the wave function psi. So if you find the solution of Schrodinger equation, then one of the restrictions on the solutions is that for it should be an acceptable wave function, it should satisfy this condition, that is normalization condition. So the solution of Schrodinger equation that satisfies this normalization condition is called a normalized wave function. Okay, it's a normalized wave function. But often it happens that you solve the Schrodinger equation and the solution need not satisfy this condition. Okay, then what else can we do? What is the next possibility? Suppose the solution of Schrodinger equation is such that, the wave function is such that this integral is equal to some finite value. Not 1, but some finite value. Then we can see that total probability is equal to some finite value. Let's say it is some let us say maybe less than 1 or greater than 1. Okay, but both are not acceptable. What we want is, if this mod psi x square is the probability density, then the left hand side is equal to total probability of finding the particle along the entire x-axis, and this should be exactly equal to 1. So when you get this as a finite value, it means that this quantity mod psi x square is no longer probability density. What we can say is that in this situation, what we can say is that mod psi x square is proportional to probability density. Okay, so in this situation, the wave function, the solution of the Schrodinger equation is such that mod psi x square is proportional to probability density. Proportionality constant can be some constant, it can be less than 1 or greater than 1. So depending upon that, if this is a situation, then what you can say is that this integral is equal to some finite value. But this is not acceptable. I mean, I'm not saying that this is not an acceptable wave function. So what we want is that this is not enough. Okay, not, let's say, not enough. This situation is not enough. What we want is this mod psi x square should be exactly equal to probability density, or in other words, this should be exactly equal to 1. If this is exactly equal to probability density, we know that the left hand side is exactly total probability, and total probability must be 1. So now this, if the integration, if this is the situation, then this is not total probability. Okay. So naturally, this integral is equal to finite value is not a statement of normalization condition. So we want to bring in the normalization condition here. So we can say that we want to make this as an equation. We want to make mod psi x square is equal to probability density. Then we want to make this is equal to exactly 1. So how do we do that? It's very easy. We know that you can make this equal to probability density by introducing a proportionality constant here. Okay, another way of saying is that you can make this integral is equal to 1 by whatever be the finite value here, you can divide throughout with that. Okay, so let us look at here. So this type of a wave function where this integral is equal to finite value, or mod psi x square is proportional to probability density, this is called an unnormalized wave function. Unnormalized wave function. Okay, this is not normalized, unnormalized wave function. So we want to make it a normalized wave function. So how do we do that? So let me say this integral is equal to okay, it's equal to some finite value. This finite value, let me call it as some mod b square. where b is in general complex. Mod b square is a constant, and where b, this quantity b is in general complex. So in order to make the right hand side equal to 1, what we can do, we can divide throughout with mod b square. So let me divide. So let us say 1 divided by mod b square. So mod b square, let me write as b star b. Okay, b can generally be complex. And this mod psi x square, let me write as psi star psi. And when you divide throughout with mod b square, right hand side is 1. Now here, let me write this b star. Let me combine this b star along with psi star and b along with psi. Then this integral you can write as psi star by b star, which is psi by b star psi by b dx equal to 1. Okay, now let this 1 by b equal to some other constant a, which is also a complex quantity in general. If b is complex, then a also is complex. Then this integral will become a psi star a psi dx equal to 1. Okay. So we can write integral a psi star a psi, which I can together write as a mod a psi square dx equal to 1. Right? Suppose this, so what we have done here is, look at this equation and this equation. This was an unnormalized wave function, and this integral is equal to some finite value. So what we have done here is, you have multiplied the wave function with some constant a, okay, which also in general it is complex, so that now the wave function is redefined. Okay, now the modulus square of this a psi square is exactly 1. So so let us say this a psi is equal to some psi 0, some new wave function. Then what you get is compare this equation and this equation. This is an unnormalized wave function where this integral is equal to some finite value. Now when you multiply it with some suitable constant, what you get is the normalization condition. Okay, so this is called normalized wave function. Psi 0 is called normalized wave function. Okay, so from an unnormalized wave function, we can get a normalized wave function by multiplying with a suitable constant, and this constant a is called a normalization constant. How do we find the normalization constant? By applying this condition, and this condition is called normalization condition. So for an unnormalized wave function, this is the situation. The integral is a finite value. You can make it exactly equal to 1 by multiplying with a suitable constant, and this constant you can evaluate by this equation, from this condition, normalization condition. So again, once you multiply the wave function with a suitable constant and evaluate its value by applying the normalization condition, what you get is a normalized wave function. So always the first step is from the Schrodinger equation. Once you get the solution, the first step is normalize it. You have to normalize it. Only then you can say that. Now in this case, you cannot say that mod psi x square is equal to probability density. At the most you can say is that mod psi x square is proportional to probability density. But in this case, it is exactly equal to probability density. So dividing with this constant is equivalent to introducing a proportionality constant in the expression that mod psi x square is proportional to probability density, where you are introducing a proportionality constant. It's the same thing that we have done here. Okay, so So I have said that the first step is to convert an unnormalized wave function into a normalized wave function by uh, using the normalization condition and by evaluating the normalization constant. Now this type of a wave function, this is possible, or this normalization is possible because the solution of the Schrodinger equation is such that this integral is a finite value. Okay, so this is an unnormalized wave function, but still it is a normalizable wave function. Okay, so a wave function that satisfies this condition is an unnormalized wave function. You can convert it into a normalized wave function through this condition by applying the normalization condition. Or we can say that this wave function here, this wave function, even though it is unnormalized, it's a normalizable wave function. So what is the condition for a normalizable wave function? The condition for a normalizable wave function is that this integral should be equal to at least a finite value. In other words, this integral should not be infinite. It should be a finite value. If it is a finite value, it's a normalizable wave function, and even though it is unnormalized, you can easily make it normalized by applying the normalization condition. So one of the restrictions on the solutions of Schrodinger equation is that the wave function that we obtain should be a normalizable wave function. Mathematically, it means that this integral should be a finite value. We can also say that it's a normalized wave function, or another way of saying is that this integral is a finite value. This integral is a finite value. What we have done here is we are integrating the square of the wave function. Okay, or not exactly square, modulus square of the wave function. So this we can succinctly say that the wave function should be a square integrable wave function. These are the same thing. These are not different. They are the same thing. We are doing stating in different ways. That's all. It should be a normalizable wave function. In other words, it should be a square integrable wave function. In other words, this integral should be a finite value. Okay. Now, mathematically, if you look at this, this integral, the requirement, this restriction that this integral should be a finite value, imposes two conditions on the nature of the wave function. What are these conditions? So as we have been saying, a normalizable wave function should satisfy this equation. Okay, it should be a square integrable wave function, or this integral should be a finite value. Now this imposes two conditions, two restrictions on wave function. One is that the wave function should be finite. At all points. At all points on the x-axis. We are talking about a particle moving along the x-axis, one-dimensional situation. So at all points along the x-axis, that means in the domain of this integration between minus infinity and plus infinity, the wave function should be finite. This is clear. Only if the wave function is finite, this integral gives you a finite value. Where at any point, if x equal to, let us say, x0, if the wave function goes to infinity, this integral will not give you a finite value. So the wave function should be finite at all points. This is one condition for this integral, for it should be a square integrable. Second is that as x goes to plus or minus infinity, psi of x should fall to 0. Psi of x should go to 0 faster than mod x raised to minus half. As x goes to plus or minus infinity, psi of x should go to 0, and the rate by which psi of x goes to 0 should be faster than this quantity, mod x raised to minus half. Okay, mod x comes because we are taking both the positive and negative values. of x. That's why the idea is that it should be go to 0 faster than the magnitude of x, 1 by square root of the magnitude of x. Okay, that's the idea. This is directly clear from this integral to be finite. Wave function should be finite at all points in the domain of integration. What about this? How do we get this? Okay, let us spend a little more time on this rate by which wave function should go to 0. Let's consider this integral. So integral from some x0 to infinity mod psi of x square dx. Okay, I just take one of the limits as finite, the other as infinity. Let us see what happens when this integral should be finite when x goes to infinity. That's a condition. Consider this integral, and now let this mod psi of x square is equal to x raised to n. Okay, it's some function of x, so let me take x raised to n, where n is a real number. Then what you get is integral x0 to infinity x raised to n dx. So let us see what are the values of n for which this integral becomes infinity. Then from that we can deduce the condition for this integral to be finite. Okay. Okay, so let me take a different value. Suppose n is greater than or equal to 1. If n is equal to 1, what you get? Integral x dx. When you integrate, you have x square by 2. Putting upper limit to infinity, you get the value of infinity. So x equal to 1 will not help. X greater than 1, definitely you get infinity. So for this, you get integral is infinite. Or yeah, integral is infinity. Or we can say integral gives infinite value. It's no longer finite. Okay. What happens when n equal to 0? When n equal to 0, you have x raised to 0, which is 1. So you have integral dx, but integral dx is x. Again, putting the upper limit, you have infinite value. So integral gives infinite value. What happens when n equal to minus 1? Let us look at this. When n is equal to minus 1, what you have is integral x raised to 0 to infinity, n equal to minus 1. So x raised to minus 1 is 1 by x. So you have 1 by x dx. And integral of 1 by x is natural logarithm of x, putting the limits from 0 to infinity. Now putting in the upper limit, again log infinity is infinity. So answer is infinity. Log 0 is 1, but log infinity is infinity. So again infinity. So we can say that n greater than or equal to 1, or n equal to 0, or n equal to minus 1. For all these things, this integral gives infinite values. Now you can attempt this. You can show that when n is, so we can conclude this for n less than minus 1, this integral gives finite value. This you can show by taking some value less than minus 1. Okay, so the condition is that for n greater than or equal to minus 1, this integral gives infinite value. For n less than minus 1, this integral gives finite value. Okay, we can get this result at the first part. We can get it in another way also. Suppose we do this integration, then what you get is integral of this one. What you get is x raised to n plus 1 divided by n plus 1 from x0 to infinity. Now it's clear that when n is greater than or equal to 1, this will be infinite. n is equal to 0, you have x here, it will be infinite. Now when n equal to minus 1, numerator is 1 because x raised to 0 you have, but when n equal to minus 1, denominator becomes infinite. I mean denominator becomes 0, so you have 1 by 0, then it is again infinity. So from this also you can conclude that for n greater than or equal to minus 1, the value is infinite. On the other hand, if n is only slightly less than minus 1, you get a finite value. For example, you take n is equal to minus 1.1. It can be any real number. You can take n equal to minus 2, or let us say n equal to minus 1.1. If n is equal to minus 1.1, denominator is minus 0.1. Here what you have is x raised to minus 0.1. X raised to minus 0.1 means 1 by x raised to 0.1. So x has gone to the denominator. So putting n equal to infinity, you have 0 value. For the upper limit you have 0 value. For the lower limit you have some finite value, 1 by x0 raised to 0.1. So the entire thing is finite. So we can say that for n less than minus 1 you have finite value. Okay. So we can conclude that this quantity integral x raised to n dx is finite. Okay, this is equal to finite if x raised to n goes to 0 faster than x raised to minus 1. Okay, n should be less than minus 1. That means x raised to n should go to 0 faster than x raised to minus 1. Okay, it should be like faster than x raised to minus 1. It means that the power or the value of n should be less than minus 1. That's the idea. So here we have put psi x square equal to x raised to n. So I can say from this one, this is finite, or this integral is equal to finite if mod psi of x square goes to 0 faster than x raised to minus 1, or which implies psi of x goes to 0 faster than if psi of x goes to 0 faster than x raised to minus half. If mod psi x square should go to 0 faster than x raised to minus 1, psi of x should go to 0 faster than x raised to minus half, as x tends to infinity, that I have to add here also. Okay, so for this integral to be finite, it becomes finite if this integrand psi mod psi x square it falls to 0 faster than x raised to minus 1 as x goes to infinity, or psi of x should fall to 0 faster than you just take this square root on both sides. Okay, faster than x raised to minus half as x goes to infinity. Now when x goes to plus or minus infinity, you have to take the modulus of x here. You have to take just the magnitude of x here. So in general, when you consider both limits, you can say that psi of x should fall to 0 faster than mod x raised to minus half as x goes to plus or minus infinity. So this is how we get this condition. Okay. So for the integral to be the wave function to be normalizable or square integrable, or for this integral to be finite, there are two restrictions on the wave function. One is that the wave function should be finite at all points in the domain of integration. That means along the entire x-axis in our discussion. Second is that the wave function, as x goes to plus or minus infinity, the wave function should go to 0. Okay, at what rate? Faster than x raised to minus half. Now again, look at this second condition. Let us. We have been talking about one-dimensional situation. Okay, wave function depends only on x. So what is the nature of the second condition when we consider two-dimensional wave function and three-dimensional situation, two-dimensional motion and three-dimensional motion? When the wave function depends on two variables or three variables, can we? Is there any modification in this condition? Wave function should go to 0 at the boundaries as x, y, z goes to infinity, plus or minus infinity. But what is this variable? At what range? How do we write the normalization condition in two-dimensional case? So we are considering two-dimensional case. So what is the normalization condition? Now the wave function depends on two variables. So we should write mod psi square. It's an area integral. Okay, it should be equal to 1, where this integration is over an area. Now mod psi square is probability density, but this time it is probability per unit area. Okay, so that this part is the probability of finding the particle in a small area element dA. And when you integrate over the entire area, suppose you divide the entire area into small area elements, then you get probability of, this is the mod psi square dA is the probability of finding the particle in each area element. You add them together or integrate, then you get the total probability of finding the particle in the entire area, maybe in the entire xy plane, and this should be equal to 1. So this is a normalization condition in two-dimensional situation. So what we were asking is here this for this integral for a normalizable wave function, then this integral should be at least equal to some finite value. Then we can make it 1 by introducing a suitable normalization constant. So for this integral to be finite, again we know as wave function should go to 0 as we go to the boundaries. Then but in at what rate? That's what we want to find out. So in order to find out that, let me use polar coordinates instead of Cartesian coordinates. Let me use polar coordinates. So r and theta. So psi is a function of r and theta, and area element we can write in terms of r and theta. And we know that in polar coordinates the radial variable goes from 0 to infinity. We are in a plane, and the theta variable goes from 0 to 2 pi. Okay. So this integral becomes integral 0 to 2 pi and integral 0 to infinity. This is for theta variable and this is for r variable. And psi is a function of r and theta, and area element is r dr d theta. This should be equal to 1, or this should be equal to some finite value. So what is the restriction on how fast should psi goes to 0 when you go to the boundaries? That is the question. And here it is the radial variable that goes up to infinity. Okay, theta variable value varies from 0 to 2 pi. So let us look at this integral first. Integration over radial variables first. Okay, so integral 0 to infinity mod psi r theta square r dr. Consider this integration first. What is the condition for this integral to be finite? So there is only one variable here. When there is only one variable, integration is over only one variable. We have already discussed the condition. The condition is that the integrand should go to 0 faster than, let us say the single variable is x. Then the integrand, remember the earlier situation of integration along the x-axis. Then what we found is that the integral was integral mod psi x square dx should be finite. And what is the condition? The integrand mod psi x square should go to 0 faster than x raised to minus 1. So here, this is also an integration along a single variable. What is the condition for it to be finite? The integrand should go to 0 faster than r raised to minus 1. Instead of x, we are using r here. But what is the integrand here? Integrand is not simply psi square, but mod psi square into r. It should go to 0 faster than r raised to minus 1. Okay, which means that psi square should go to 0 faster than, take this r to the right side, it should go to 0 faster than r raised to minus 2, which means that psi r theta should go to 0 faster than, you can take square root on both sides, it should go to 0 faster than r raised to minus 1. So for this integral to be finite, the condition is that psi should go to 0 faster than r raised to minus 1. Okay. If psi satisfies this condition, then it is guaranteed that the other integral, integration over theta, will be finite. Okay. So we need to worry about the situation only when the variable itself, the radial variable, goes to infinity. So the condition in two-dimensional situation is that the wave function should go to 0 faster than the variable r raised to minus 1. Okay. This is slightly different from the one-dimensional situation where the wave function should go to 0 faster than x raised to minus half. Okay. So let us consider the three-dimensional situation also. So in three-dimensional situation, what is the condition here? We can rewrite the equations faster here. It should be a volume integral. Integration should be over a volume. What is psi square now? It is probability per unit volume. So this gives you, you multiply this with some volume element. So you have a three-dimensional motion. Particle is moving in 3 dimensions. So what you do is this 3-dimensional space you divide with small volume element dv. This is probability per unit volume. So you multiply with the volume element, what you get is probability of finding the particle in each volume element dv. You add all these probabilities, mod psi square dv plus mod psi square dv plus mod psi square dv, that is this integral. And this total integral should be 1. This is the normalization condition. So our task is to ask the question, what is the condition for this integral to be finite? At least it should be finite, only then we can make it normalized. Okay. So again I am using spherical coordinates. Because there is only, in spherical coordinates r theta phi, there is only one variable that goes to infinity, which is radial variable. So it is easier to generalize. So when we use spherical coordinates, what is the change here? The wave function depends on r theta phi, and there are 3 variables, r theta and phi, and r theta varies from 0 to 2 pi. We know that phi varies from, theta varies from 0 to pi, phi varies from 0 to 2 pi, okay, and again r varies from 0 to infinity. And what is the volume element? It is r square dr sin theta d theta d phi. R square dr sin theta d theta d phi. This is the volume element, and this should be equal to 1. And again, here only one variable goes to infinity, radial variable. So let us consider this integral first. Again, just like in the one-dimensional situation, this is integration over a single variable. So what is the condition for this integral to be finite? The integrand should go to 0 faster than the variable raised to minus 1. Okay. What is the integrand here? This time it is mod psi square into r square. And this should go to 0 faster than r raised to minus 1, which means that, okay, let me put psi r theta phi here. Okay. So mod psi square should go to 0 faster than, take this r square to the right side, divide with r square. So r raised to minus 1 divided by r square, what you get is r raised to minus 3. So mod psi square should go to 0 faster than r raised to minus 3. Which means that take square root on both sides, psi should go to 0 faster than r raised to minus 3 by 2. So in 3-dimensional situation, the condition for this integral to be finite, for to be wave function to be square integrable or normalizable, is that the wave function should go to 0 faster than r raised to minus 3 by 2 as r goes to infinity. In the 2-dimensional situation, forgot to specify this. It should go to the wave function should go to 0 faster than r raised to minus 3 by 2. Not necessarily at all points, but when as r goes to infinity, it should definitely go to 0 faster than r raised to minus 3 by 2. So this condition should be specified in the two-dimensional situation also. In the two-dimensional situation, it was like r wave function should go to 0 faster than r raised to minus 1. So let us just consolidate the three conditions, and let us try to get a general expression for that. Okay, so let us summarize. In the one-dimensional situation, psi should go to 0 faster than x raised to minus half as x goes to infinity. Okay, when x goes to plus or minus infinity, we have to put a mod here. That's the only difference. In two-dimensional situation, we found that psi should go to 0 faster than r raised to minus 1 as r goes to infinity. In three-dimensional situation, psi should go to 0 faster than r raised to minus 3 by 2 as r goes to infinity. So let us generalize. Suppose it is n-dimensional. Okay, if it is an n-dimensional situation, we can say psi should go to 0 faster than r raised to minus n by 2 as r tends to infinity. Put n equal to 1, you get this. Okay, instead of r, you are saying it as x if it's a single variable. Put n equal to 2, you get this. Put n equal to 3, you get this. Okay. So this is the general condition. Depending upon the dimension, the wave function should go to 0 faster than r raised to minus n by 2. So we were discussing the normalization of the wave function. What is the idea of normalization? Normalization means that it's simply a statement that total probability of the system should be 1. In the entire domain, the total probability of the system should be 1. So this arises from our probability interpretation of wave function. We demand that mod psi square is probability density. Depending if it's a one-dimensional situation, it is probability per unit length. In two-dimension, probability per unit area. In three-dimension, probability per unit volume. But if mod psi square is probability density, then integral of mod psi square over the region, whether it is one dimension or two dimension or three dimension, that integral should give you the total probability of the system in that region, and this total probability should be 100% or 1. This statement is called normalization of the wave function. So the condition is that the solution of Schrodinger equation to be an acceptable wave function, it should satisfy this normalization condition. That means at least we should say that at least it should be a normalized, it should be a normalizable wave function. Normalizable wave function means that integral should be integral mod psi square dx or integral mod psi square dA or integral mod psi square dV in three dimension. This integral should be finite. Then we say that it's a normalizable wave function or square integrable wave function. If it is finite, it is not now normalized, it remains unnormalized, but we can multiply it with a suitable constant, and applying the normalization condition, we can evaluate this constant. This is called normalization constant. If we multiply the unnormalized wave function with the suitable normalization constant, we get a normalized wave function. But for all this to happen, that integral should be a finite value. Such a wave function is called normalizable wave function. It has the potential to be converted into a normalized wave function. Now, for this integral to be finite, we have seen that there are two restrictions on the wave function. One is that the wave function itself should be finite at all points in the domain. Second is that as you go to the boundaries of the domain, as the variable in the integration in the domain goes to infinity, the wave function should go to 0. And at what rate? At a rate faster than we can say r raised to minus n by 2. which whatever be the variable that goes to infinity, the wave function should goes to 0 faster than r raised to minus n by 2, where n is the dimension in which you define the wave function. In the one dimensional case, the wave function should go to 0 faster than x raised to minus half. In the two dimensional case, as the radial variable goes to infinity, or whichever be the variable that goes to infinity, the wave function should go to 0 faster than r raised to minus 1. In three dimensional case, r raised to minus 3 by 2, like that. So this is the idea.